Question 9 from paper 2 of the 2024 Higher Physics examination from the SQA. A student uses the apparatus shown to investigate the photoelectric effect. You can see we've got an ultraviolet lamp, that's this positioned here. We've got a quartz window which allows ultraviolet radiation to pass through. It's surrounded in a vacuum box, and we've got a platinum wire mesh here, a zinc plate here, and of course it's connected to a micro ammeter and a DC supply, so that this part here is going to be plus, and we know that the ultraviolet is going to shine on the zinc plate and hopefully release electrons which will be attracted up to this plate because it is plus. Anyway, let's read on. When the lamp is switched on, the ultraviolet UV radiation passes through the quartz window and the wire mesh and is incident on the zinc plate. A current of 5.00 microamps is produced by the circuit. And for 3 marks in part AI, it says the lamp emits ultraviolet radiation with a frequency of 1.25 times 10 to the power 15 Hz. And we've got to calculate the energy of the photon of ultraviolet radiation. Well, we know we go to our relationship sheet, and we know the energy of a photon is related to its frequency by h times f, where h is Planck's constant. So we know that h is going to be equal to 6.63 times 10 to the power minus 34 joule seconds, and we're dealing with a frequency of the photon, and that's going to be equal to 1.25 times 10 to the power 15 Hz. So all we have to do is multiply those two numbers together. So we have the energy of the photon is going to equal to HF is going to be 6.63 multiplied by 10 to minus 34 joule seconds, and we're going to multiply that by the frequency, which is 1.25 times 10 to the power 15, and remember Hertz is 1 upon the period, so it's going to be seconds to the minus 1, so you can see the 2 seconds cancel out and you're left with the energy of joules. Do that in your calculator and you're left with the energy of that incoming photon is equal to 8.29 times 10 to the minus 19 joules. That's the energy of the incoming photon. Question 9a, part 2. The work function of zinc is 5.81 times 10 to the minus 19 joules, and we have to explain why ultraviolet radiation with a frequency of 1.25 times 10 to the power 15 Hz produces current in this circuit. Well, to produce current in the circuit, you must eject photoelectrons away from the metal, and we can imagine the metal surface to be like this in terms of a energy diagram, not a physical diagram but an energy diagram, and the work function tells you how much energy is needed to escape from that well, if we can think of it that way. So the work function is going to be 2.48 times 10 to the minus 19 joules for this electron here. So if this electron gains that amount of energy, it can escape up and out of the well. That's really what's happening here. Now the photon that's coming in, we worked that out in the previous question. The photon that comes in and is absorbed by the electron has got 8.29 times 10 to minus 19 joules. So it's got an excess of energy. So the photon will be completely absorbed, and we have the electron using 2.48 times 10 to the power minus 19 joules to get out there, and it's also going to have some excess energy in the realm of 5.81 times 10 to the minus 19 joules. So that will be in fact the photon's excess energy, which will appear as kinetic energy. So if you're 2 marks, that's your explanation. The ultraviolet radiation with frequency 1.25 times 10 to the power 15 Hz has got more than enough energy to overcome the work function, which is the energy required to be released from the metal or to get out of the energy well, so to speak. And it's got excess energy because the 2.48 times 10 to the minus 19 joules is going to be used up to get the electron out of the metal. Is going to appear as excess kinetic energy of 5.81 times 10 to the minus 19 joules. Question 9, continued part B. The student now moves the ultraviolet lamp closer to the quartz window. Now it states whether the current in the circuit increases, decreases, or stays the same, and you must justify your answer. Well, if we bring that ultraviolet lamp closer, it's becoming closer to the zinc plate, and if we move it closer to it, that means that we're increasing the irradiance of the light falling on the zinc plate. Remember, the radiance is the power divided by the area, and the power is the amount of energy per second. So really, we are bringing a lot more photons to strike the zinc plate when we bring that ultraviolet lamp closer. Now that just means that more photons per second will be arriving on a zinc plate, and if more photons are arriving on a zinc plate, then this means that more photoelectrons will be ejected from the metal surface. And if there's more photoelectrons being ejected from the metal surface, then this means that more photoelectrons being attracted to the wire mesh, and that means more charges per second arriving, which means an increase in current. So basically you're going to get an increase in current if you bring it close to the zinc plate. If we have a picture before, we can see that the ultraviolet lamp is giving off photons in all directions, and that's the zinc plate. But moving the lamp closer, you can see that more photons per second are going to be arriving on the zinc plate. And if more photons per second are arriving, which means the radiance is getting bigger, you're going to release more photoelectrons, which will result in a bigger current flowing in the circuit. So the current will increase. Question 9, continued part C. The student now reverses the polarity of the DC supply, and we have to state the effect this change has on the current in the circuit. Let's go to the simulation by PHeT, that fantastic site, and you can see it's a very similar setup. You've got ultraviolet light shining onto a zinc plate, and you can see this is going to be the situation before we reverse the polarity. So this is going to be plus, and that's going to be minus there. And the polarity is 1.5. You can see we have a current flowing in the circuit. Now, what I'm going to do is reverse the polarity by just making that negative. So I've changed the polarity round, and let's see what happens. We get absolutely nearly no current. So the current's obviously decreased. You can see why that's the case, because if I've reversed the polarity, this part of the circuit is negative. So the electrons leaving the zinc with quite a lot of kinetic energy are going to be flying across here and then going to be repulsed back along here. So only those electrons with the highest amount of kinetic energy will actually make it across the electric field if the polarity is changed. So the answer to that is if the polarity is changed depending on the size of the polarity of the circuit. In fact, if I could make that back to 0, back to positive, and maybe increase it a wee bit. So if I'm going to increase this to maybe say 3 volts, and you can see the electrons are scooting across from the zinc over to the plate. Now if I reverse the polarity of that and make that minus, and you can see, well, most electrons don't get there. It's only the most energetic one which gets there. The rest of them don't get there at all. So the effect of that would be to in fact reduce the current and almost stop the current from flowing.